Welcome to Darwinian Bytes, where we explore the world of evolution and emergent behaviors through computer simulations. In this video, we build on the previous simulation by improving the movement rules. We're going to try several different options, mainly what would be considered naive movement rules. That is, rules that are fairly simple, and that although they may seem good at first glance, they really aren't that good. But it's important to go through this step so that we can properly understand why they aren't that good. This will in turn lead us in a better direction on how to make the more sophisticated and smart movement rules. But before I get into the details, I'll first just give everyone a quick refresher on the rules of the simulation up to now. I think it's both a good reminder to those who have seen the previous videos, as well as the new people who are just joining us now. So the rules of the simulation are: entities can be either the color red or blue. Entities can be of size 2 to 20 pixels. Entities can consume smaller entities if they are a different color. If they are the same size, then the winner is randomly selected. Consuming an entity increases your size, and being consumed by an entity decreases your size. When entities reach a size of 20, they can spawn. The newly spawned entity is of size 10, and the old entity drops to size 10. Entities that drop to size 0 die and are removed. Entities have an eyesight of 100 pixels. In the previous video, I had said 200 pixels, but it's actually 100 pixels. If there are no smaller entities within its eyesight, the entity will randomly move between 1 to 7 pixels in a random direction. If an entity sees a smaller enemy entity in its eyesight, it will move in that direction. In the previous videos, it would move between 0.5 to 3.5 pixels, whereas from now on, it will move 1 pixel. There was previously no avoidance rules, meaning if a bigger enemy is within its eyesight, it is not even aware of it and completely ignores it. One extra thing I should mention before we start getting into the new movement rules is that I've adjusted the color of the eyesight. Specifically, the color of the eyesight range is now white instead of yellow when the eyesight is visible. More importantly though, the color changes with the behavior of the entity. If an entity seeks another entity, it changes to green, and when it avoids another entity, it becomes red. If it's both seeking and avoiding at the same time, then it becomes yellow. Again, and as I mentioned at the beginning of the video, we're going to start with some pretty naive movement rules and expand from there. It's a lot easier to understand if we try the simpler options first to expose their weaknesses and see where they falter, so that we know how and why we have to improve them. A quick little spoiler, and as an example of a movement rule we're going to try, is to have the entities move towards their nearest smallest enemy while at the same time avoiding their nearest larger enemies. Something that's going to be a little different in this video than the other videos is that I'm also going to include some programming code from behind the simulation. In more detail, what I'll do is first quickly explain a movement rule, then I'll implement it in code, finishing by going over how it affects the simulation. If you want to skip over the programming parts, and I'm going to try to keep them as simple as possible, you can nevertheless just skip the middle sections of each movement rule. On that note, please let me know in the comments if you'd like me to keep the programming sections in the videos or not. And if you prefer the programming sections, please let me know if you want more or less details. With that in mind, I'll just quickly say that this simulation is built in the Java programming language using the game development framework called libggdx. Now, don't worry if you're not familiar with either, it's not really that important or even really needed. I'll only be showing code that's at a pretty high level, and even then, I'll be keeping it to only the interesting parts. It should be very language agnostic. Like I said, I'll try to keep it simple and easy. We just have one more thing I need to go over before we get started. I need to take a quick moment to explain what vectors are and at least how we'll be using them for our purposes. Otherwise, vectors can easily be a video just by themselves if I wanted to try to fully cover them. If you want to learn more about them though, I'm including some links in the description. The simplest way to look at vectors is that they are a combination of a magnitude and a direction. In our case today, magnitude will be length, so I'll mainly just say length from now on. So for example, I could say a vector represents me going to the right for 3 steps. The direction is the right, and the length is 3 steps. Vectors can be used to represent movement and velocity as well, so instead of going to the right for 3 steps, it could be at a speed of 3 steps per second. But for our purposes, we're going to just say that they represent a length, which in the simulation will be pixels rather than steps. Let's take it up a notch, and instead of moving just to the right, let's say instead I move diagonally to coordinates 3, 4. How can I represent this vector? For now, I'm going to skip the angles and just say it points to the upper right at some angle. But getting back to the length, how many steps is that? It's not 3 steps, and it's not 4 steps, and it's not also 3 plus 4 equals 7 steps. As in, if we were to walk to that coordinate, we would go directly to it. So how many steps is that? The good news is that it's pretty simple to calculate. Most of you have probably heard of Pythagoras' theorem to calculate the lengths of a triangle where a squared plus b squared equals c squared. We're going to use that to calculate the length of our vector. Plugging in the numbers into the formula, we get 3 squared plus 4 squared equals c squared. We can then simplify this to 25 equals c squared, which gives us the answer of c equals 5, meaning the length of the vector is 5. And in our case, since we're using steps, that means it's 5 steps in the direction of the arrow. In all honesty, we don't even really need to know how the math is calculated because it's all automatically done for us in the vector libraries. What's more important is to understand the concepts. As in, I'm not even going to show how the angle is calculated. It's not really that important at the moment. I only included the math for the length because knowing it can give you a clue on how to make more advanced movement rules. Not to get too far ahead, but maybe we might want to give different movement rule priorities based on the distances between the entities. But that's for the next movement video. You might be asking yourself, what's the benefit of using a vector rather than just a direction and angle, which is a very good question. It's just a data point after all, just in a different format. So why use vectors? And if that was it, then you'd be right. There's very little benefit, if any at all. But what if we want to do more than that? Although I haven't covered this part of vectors yet, what if there are 2 smaller entities and we want to go somewhere in between them, between going to just one? In this case, we can add the vectors for both enemies together and get a middle point between them. Don't worry, adding vectors is actually very simple, and most of it is done for us in the vector libraries. I'm just going to cover the concept with some visuals and focus on what's important for us, such as getting the direction between the 2 entities. To do this, we put the vectors one after another, head to tail. If you notice, the combined angle is now right in between the 2 enemies. It's really as simple as that. The only thing is that although we get the direction, that the distance is way off. We're going right past both enemies. Also, an entity can't just leap that far in one step. And imagine now if we had a 3rd entity, the distance would be even further. So although we have the right angle, we don't have the right distance. It's way too big. So how do we fix this? We fix this through the concept of normalization. We're going to skip the math here too. The key concept is that normalization reduces the length to 1 unit, almost like saying a max of 1 step. From here, we would apply a scale. So for example, if our max movement was 3 steps, we do 1 movement times 3 steps equals 3 steps of movement. But to keep things very simple in this video, we're going to keep the movements to 1 pixel so that we can just ignore scaling entirely in this video. As maybe a quick spoiler, because I don't want to reveal too much yet why today's movement rules are considered naive, imagine what would happen if the 2 entities are on the opposite side. The average direction wouldn't be ideal. That being said, we're almost done with vectors. We have one last concept to cover. In addition to adding vectors, we can also subtract them. If we want to avoid something, we probably want to go in the opposite direction, which means we'd want to subtract a vector rather than add one. We've just covered the basics of vectors. We can do a lot more with them, and they can be extremely powerful. But for now, that should be enough for us to implement the movement rules we want for this video. Before we get into the actual movement rules themselves, we should first set up and program a bit of the code and framework for it. we're only going to focus on the core movement code to keep the complexity down. The way it's programmed is that the simulation runs the movement code for each entity every cycle of the simulation. The movement code is comprised of a movement algorithm, which is then further defined into the specific movement algorithms, such as move towards the smallest enemy, or move towards the nearest small enemy, and so on. The reason for the intermediate step is so that we can share the common code between the different algorithms in a parent class and not have to rewrite it every time. In fact, it's what's called an abstract class, which means a parent class that requires some things to be implemented. But that's more details and less important for today. Let's start at the top with the movement class itself. The code in this class is called every cycle of the simulation. In it, we define which movement algorithm we're going to use for this simulation run. If you're not as familiar with object-oriented programming, what we're doing is creating a generic movement algorithm and then assigning a specific one to it. In this case, move towards nearest enemy. The benefits of doing it this way is that we can change the movement algorithm later to any other one, and we just need to change one line of code. We don't need to mess around with anything else. The code for the movement class boils down to doing three things. First, we have to save the current position of the entities before we do anything. This is very important because we have to wait until we're done all the movement calculations before we can actually move the entities. Otherwise, for example, an entity could move away from another one's eyesight before it even had the chance to see it and move towards it. Therefore, we need to do all the calculations first, and only after everything has been calculated can we perform the actual movements. Now that we've saved the initial positions, we need to calculate the actual movements themselves. The calculated move is then saved to the next x and next y values. And lastly, we need to apply the calculated moves. So just to quickly recap, we need to save the original position, calculate the moves, and then make the actual moves. Now that we know how the movement works, we should dig a little deeper into the move algorithm. That is the parent of the specific movement algorithm class, like the move towards smallest enemy. This code is broken down into two parts. The first part is the move method that we just talked about, where we calculate the move. In this method, we first get a list of all the entities within its eyesight. We don't discriminate between friendly or enemy entities, we just get every single entity within its eyesight. If there are no entities in its eyesight, then we move randomly. If there are entities within the eyesight, then we call the move with entities in eyesight method, which is implemented by the specific movement algorithms, such as again, move towards the smallest enemy. Just a quick reminder that at this stage, we don't know if the entities are friendly or enemies, just that there are entities. We have to leave this distinction to the actual movement algorithms. Don't worry, this will make more sense soon. The second part of the movement algorithm, at least that we're going to talk about in this video, is more of a helper method than anything else. The reason it's here is so that it can be reused by the different movement algorithms. It saves us from rewriting the same code over and over. This also means that if we change it, then it automatically updates all the different movement algorithms for us. Again, there are several helper methods, but the key one we care about for this video is the one called move entity relative to other entities. It does very much what you think it does. It moves entities relative to each other. It does this by getting the vectors and then using the vector math we covered before to calculate the final movement vector, which is then used to move the entity. In more detail, it takes in the current entity we're looking at, combined with the list of all the entities it wants to move towards to, and all those it wants to move away from, then using vector math gives us the direction and distance to move. This is why we covered vectors earlier in the video. To program this, the first thing we do is create the vector for our current entity, as we'll need it to create a vector to the other entities in its eyesight. We then create a vector which we'll be using to store the combined total of all the vector math we're going to be doing. The next two lines are where we add all the vectors to the combined direction vector that we just created. The first line loops through each entity that we want to go towards and adds it to the combined direction vector. The second line does the same, except it subtracts them from the combined direction vector, since we want to go away from them instead of towards them. The next step is to normalize the combined direction vector, If you remember from the previous vector section of the video, when you add or subtract vectors, the angle will be correct, but the length may be off. Normalizing adjusts the length to be 1 unit of measurement, which in our case is 1 pixel. Calling the normalize method takes care of this for us. After that, we then add the new combined vector to the entity's next position values, that is next x and next y. Again, keep in mind we don't want to move the entities until after all the moves for every entity has been calculated. As a quick tangent, and this is a very small detail, but the reason we put this code in the if condition is because there's no point in running this code if the vector has no length, because then there's no movement. We could push this outside of the if statement, which would also be correct. However, and this is a bit more advanced, by putting it inside the if statement, we can get a slightly better performance in comparison. It might seem trivial, but over 1,000 entities times 30 frames per second, it can add up. You want to be careful not to add premature optimizations when programming, but in this case, I think it's worth it. The very last step, and I almost omitted it, but ultimately I decided to leave it in, is the wrap entity position call. This deals with any wrapping of the map calculations. I figured some of you may be wondering how this is handled, especially if after doing all the calculation, an entity goes off the edge of the map. Well, this is where and how it's handled. Specifically, this method checks the positions after the calculations, and if it goes over the edge, it corrects it and wraps it around the map. From here, we go into the specific movement algorithms, like move towards the smallest enemy, which will be covered in the individual movement sections coming up next. That being said, one of the big benefits of this setup is that when we implement a specific movement algorithm, we no longer really need to concern ourselves with the details we just covered. It's all automatically taken care of for us in the code. As a result, we can just focus on the specific movement for an entity. And as an added bonus, the code is going to be a lot smaller and simpler. Let's start with one of the simplest movement rules, which also just happens to be the one that was implemented in the previous video. That is the movement rule where the entities move towards the smallest enemy within its eyesight. Otherwise, it moves randomly. We're also going to ignore any enemies that can consume it, just like in the previous video, to keep everything the same. Well, there's going to be one difference from before, in that instead of moving towards an enemy between half a pixel to 3.5 pixels, we're instead going to move 1 pixel per move. One quick thing is that the movements before were always either sideways or up or down, but never diagonal, whereas now they're going to be in the exact direction. The general concept is the same, but it will nonetheless have a small impact on the behavior, as you can see from this side-by-side comparison. Now that we understand the movement rule, let's go ahead and implement it in the code. If you remember from the previous section, every movement rule extends the movement algorithm. In more detail, it actually extends an abstract class called the abstract movement algorithm. The main difference we care about today between an abstract class and a normal class is that an abstract class can force you to implement a method or more, which in our case is the move with entities in eyesight method. As a quick refresher, this method is called from the main move method if there are any entities within its eyesight. The move with entities in eyesight method takes our current entity as well as a list of all the entities within its eyesight. In this specific movement algorithm, we only care about enemies. We don't care about friendly entities. And we only care about the smallest enemy. Therefore, to find the smallest enemy in our eyesight, we first have to filter out the list of entities in our eyesight. To do this, we go through our list, which in Java means we iterate through a stream. We then apply a filter to the stream to only keep the enemy entities. We of course want to filter that list further to only smaller entities than the current entity. Finally, we look at the smallest remaining entity, and if there isn't any, then we just return null. We then check to see if we have a matching entity, in which case we move towards it. And if there are no matches, then we apply a random movement. Now, you may be wondering why we can't just skip the filter to find smaller entities and instead just go straight to looking for the smallest enemy entity. Well, there's a good reason. It's because what if the smallest entity is a larger entity that can consume it? That is, there are no smaller entities, there's only one very large entity. In this case, we wouldn't want to approach it. We're not yet really trying to avoid larger entities, Rather, we're only looking for smaller entities than us, and then focusing on the smallest one of those that can be consumed. Because if we were avoiding, we would actually want to go in the opposite direction, whereas now we just apply a random movement without any care that there could be a bigger entity bearing down on it, ready to consume it at any moment. As you can see, because we took a bit of time to set ourselves up earlier, this code to define the specific movement algorithm is pretty straightforward and simple. We're of course going to be adding to this, but most of the naive algorithms we're going to cover in this video aren't going to be that much more complex. Now that we know how the movement algorithm to move towards the smallest entity is implemented, let's look at how it affects the simulation. Again, it's going to be very similar to the last video, which is why we started with this movement algorithm first. The only thing is that the seeking behavior will be much more visual and apparent because of how we adjusted the movement when seeking. With that in mind, I think it's quite interesting to see how the entities shift from randomly moving and oscillating to seeking other smaller entities to consume. It's almost like it creates an invisible boundary when it changes behaviors from randomly moving to seeking other entities to consume. Outside of that, it's very much the same. We still get large congregations at specific coordinates as they pile up on each other until eventually there's a winning color. Pretty much everything else is the same except for the speed of the seeking movement. And that's expected. That's why we started with this algorithm. It's also a good way to validate the movement framework before we start to try the different movement algorithms and get into more complex movement algorithms. The next movement rule that we're going to explore is going to be very similar to the last, where we move towards the smallest enemy, except that we're going to move towards the nearest enemy that we can consume. And similar to before, we're going to continue ignoring other enemy entities that can consume us. This might seem like a subtle difference, but it should help reduce the clustering. That is, all the entities won't all head towards the smallest entity and then pile up into a huge battle until finally one color has won. There should still be some clustering, which I'll talk about in the next section of the video, but it should be reduced. It should be somewhat spread out in some of the battles. This movement algorithm is still pretty naive and less than ideal, but we're going to leverage some of this behavior in more advanced movements in part 2 of this video, so I thought it was important to cover it now. So with that in mind, let's look at the code for this movement algorithm. You'll notice the code is almost the same except for one line. All that changes is that we swap the minimum method, where instead of getting the smallest, we now get the closest. I did put some extra code on how to get the closest entity behind the get closest entity comparator method to keep things simpler because there's a bunch of math behind it. But ignoring that, they're virtually the same. The reason it's a bit more complex than just using vector math is that we have to take into account what happens when the entities wrap around the edges of the map. In any case, the key is that the core of our algorithm only changes by one line. That's it. That's really all the changes between these two movement algorithms. How do you think this change will impact the simulation? Before the next section starts, I recommend doing a quick pause now in the video so that you can try to predict what will happen. In terms of spawning, if an enemy gets large enough to spawn, it will then split into two equally sized smaller entities, which in turn may now be smaller than one of the enemy entities it just attacked. Should this happen, the fight might be reversed and now it's being hunted. This may in turn also attract other nearby enemies that were smaller but now are bigger. That's why right on the screen you can see a perfect example of this, with the battle shifting back and forth from specific spot to moving locations and going back and forth between these two behaviors, depending on exactly where they are as they oscillate back and forth. We'll explore the other reason with a specific example because it's less obvious and definitely harder to see in a running simulation. In this situation that you see on the screen, the smallest entity is between all three blue entities, and if they're going towards the small entity, then they would all congregate at that location. However, now that they are looking for the nearest enemy, then the blue entity on the left will go towards the smallest entity just by chance because it also happens to be the nearest, and the other two will go for the other red entity. In this case, the clustering will be at a different location than if we're going for the smallest. Also, it won't be as big a cluster. But let's take this one step further. Let's place three enemy entities, each closer to a different blue entity. In this case, there will be no clustering at all. Now, once one of the red entities is consumed, the scenario will change and we may quickly see a clustering event, but most likely the clustering will also itself quickly dissipate as things keep shifting. Somewhat related to clustering, and a behavior that's completely new, is that we now sometimes see a bunch of very small entities hovering and oscillating randomly around some of the battles. Before, because they were the smallest, they would be the center and the target of the big battles. Now, however, they aren't necessarily the target anymore because they may not be the nearest enemy. And because they are so small, they probably don't have a smaller entity nearby to consume, so their only option left is to move around randomly. It's an interesting side effect that we'll want to address as we improve the movement algorithm. Another thing you may have noticed is that there are less big open spaces overall. This is because the entities all don't converge and cluster on the smallest entities, as we've just seen in the detailed example, which in turn leads to a more even distribution overall. So although this movement rule doesn't really resolve clustering, it definitely has an impact in a positive way. We'll of course want to improve on this in the future, but right now I just wanted to show you that going with the smallest versus the closest enemy does change the behavior of the simulation. That being said, have you noticed any other differences in behavior between moving towards the smallest and moving towards the closest enemy? We're now going to look at the opposite of moving towards a target and instead avoiding a target, or you could also say moving away from a target. That is to say, the entities will no longer hunt and seek enemies to consume, but rather just avoid a bad outcome for themselves. This will have an interesting side effect that causes a kind of emergent behavior, which I'll cover as an extra section for this movement. But before we get into that, the code for this movement algorithm is virtually the same as the move towards the nearest enemy algorithm except for two lines. First, the filter is smaller entity filter changes to is larger or equal entity because we now want to avoid larger enemies rather than seek smaller enemies. Secondly, the move towards entity changes to the method move away from entity because again, we want to move away from the closest enemy we find rather than towards it. That's it. Just those two lines of code need to be changed to have the entities avoid instead of seek. The biggest change in behavior is that the entities rarely ever meet each other because they're always avoiding each other. Even with fairly large populations, there's rarely ever any battles. So much so that the simulations never end, at least not within a reasonable amount of time. They still have clusters, but they're different kinds of clusters. In essence, they start to form large groupings with spaces between them equal to about the eyesight range. The shapes slowly change over time, but it's a slow progression that can take a lot of generations in some cases. The reason being is that the larger entities move around randomly if there's no one to avoid. At the same time, smaller entities will avoid the larger entities, and so they don't ever really battle. But the result is that the larger entities mostly define where the borders of the groups are because the smaller entities are generally running away to the protection of nearby larger entities. This avoid the nearest enemy movement algorithm helps reduce the large battles, but in turn it creates another problem in that it eliminates virtually all battling. So, although this isn't the movement behavior we want, we still want some kind of middle ground where entities try not to get consumed and die, but at the same time seek out enemy entities they can consume. But before we get into that, the code for this movement algorithm is virtually the same as the move towards the nearest enemy algorithm, except for two lines. First, the filter is smaller entity filter. In more detail, all I did was change the starting population from 1,000 entities to 10,000 entities. Initially, everything looks pretty much the same as you can see. It's only after about 500 generations that you can start to see something different. Around 1,000 to 1,200 generations is when it really starts to get interesting. To me, this is when it starts to resemble an animal print. I didn't expect that kind of behavior at all. The population is very stable because everyone is avoiding everyone else. The overall pattern is also very stable. It just keeps moving around. Something else that's also very interesting is that for this pattern to emerge is that it requires a certain minimum population. 1,000 entities is just not enough. What do you think is the minimum population required for this behavior to emerge? At this point, we've covered some of the more basic movement algorithms, but of course we want to expand beyond them. For sure, we want to combine both seeking and avoiding. And of course, we also want to add some intelligence to our entities. The next movement video will focus mainly on combining different seeking and avoiding rules. For example, what happens if we both seek the nearest entity we can consume while at the same time avoiding the nearest one that can consume us? Or what if we take the average of all the enemies we can consume combined with the average of all the enemies that can consume us? Movement algorithms of that nature and how they impact the simulation. In the third installment of this movement series, I'm planning to add more intelligence to the entities. Ideally, things such as predictive seeking, where instead of just going directly where the entity is at the moment, instead we now try to predict where it will be when we reach it. This is a small difference, but it can have very significant implications. For now though, I'm going to end this video as we've covered the basic movement algorithms and options, and it's already quite lengthy. But there's definitely more to do when it comes to adding movement to the simulation. Are there any specific movement topics you'd like me to cover or include in the simulation? Let me know in the comments. And on that note, don't forget to like and subscribe to see more content like this.